Welcome to the latest edition of Reimagine Mobility podcast series. I'm here with Darrell Robinette. Did I say that right?
Yes.
All right, very good. I want to make sure it's right. He works at MTU, but you also have a history with GM in the transmission group, so I assume a mechanical engineer?
Correct.
Okay, so tell us a little bit your history and how did you end up at a university?
Well, I guess you got a few minutes here, right? So I was born in Southeast Michigan and always had this curious fascination with the way things work. It's a book, I'm sure a lot of engineers still have it on their bookshelf today. My dad worked for Detroit Edison. He was a controls and instrumentation specialist. In elementary school, he took me to the power plant and he was fascinated by everything there, right? And the machinery was on scale. 1,200 megawatt coal-fired power plant. I know that's probably a swear word today saying coal, but it's what keeps the lights on for the most part in some areas of the country. But all the engineers that worked there at Detroit Edison at this particular power plant, Bell River, they're all Michigan Tech grads. And so, fourth or fifth grade, you're talking to some of these engineers and like, oh, you should just go to Michigan Tech. And that's where, I guess the Michigan Tech, going to school there, that's where that came from. But my dad always told my brother, and I have one older brother, we're going to go to college. And, so I guess that's kind of how to get to Michigan Tech. So then, of course, started at Michigan Tech. I'm only going to do an undergraduate degree. Well, then comes along a girl, right? And then, all right, we'll stay a little bit longer for some graduate school. And that grad school project was funded by Advanced Engineering Powertrain at GM.
GM, okay.
Right, and all growing up, I always said, I'm never going to go work for a car company. I don't want to work for a car company because of the strikes and the boom-bust cycle. Well, this graduate project really provided a lot of insight into what making a car really is.
Yeah.
And it's a very, very deep technical process where you leverage everything you learn in engineering school. And oh, by the way, these car companies have all these resources to do really cool engineering, right? And so, grad school's like, fine, let's go work for, GM post-graduation.
Yeah.
And that experience was just amazing. And I got to use a lot of your guys' dyno equipment and test equipment, right?
Yes.
And so get very familiar with doing very standardized and even non-standardized test procedures on dyno. Right, and so the latter part of your question, how did I end up from going Michigan Tech to GM and then back to Michigan Tech?
Full circle back again.
Well, this girl that I met, and my wife now, she ended up going to med school at Michigan State and then doing residency at U of M. And then she got a job right out of residency back at the hospital up by Michigan Tech.
Okay.
So I said, well, I should probably follow, right? And so Michigan Tech they're very keen on bringing people back from industry because we learn a particular set of skills, and we can relay that back to students so that when they join industry, they can hit the ground running. And so, right, I guess that's the way it comes full circle.
Good.
Yeah.
Very interesting.
And so now kind of get to give back to young engineers what was given to me by a lot of the faculty, 20 some years ago.
Yeah.
Right?
So how many students do you have that are in a similar position that you were that says car companies, garbage, I don't want to work there. I want to go into power plant. I want to go into aerospace. I want to go into whatever. That just like, just be open-minded. How many of those percentage-wise you think?
Yeah, it's a shocking percentage. Cars, for some students, cars today aren't as quote unquote sexy as rockets. So we have a lot of students wanting to go work for SpaceX or this, that, the other thing, aerospace. But for a number of students, we spent a lot of time convincing them that, hey, look, there's a lot of really interesting things that are going in mobility systems that are very, very techy, right? It's not, hey, I'm going to design gears, I'm going to design pistons and connecting rods, right? There's still a place for that in automotive engineering, but similar to like what we're doing on this project, it's coding, it's connectivity, it's automation, it's trying to fuse sensors together, trying to do control vehicles from the cloud. So we do have a kind of an uphill battle convincing students to go work in mobility. But once we connect them with folks in the mobility industry and they have their first taste via, podcast or their first internship or co-op, and then they're kind of hooked.
Really interesting.
Right, and we have really good hooks in with industry of these student design competitions like the SAE and GM auto drive competition that become magnets for recruiting for students, and it also gives them an inside view. And I'll put you on the spot a little bit. If you got opportunities where we can put students in, right, you're going to find that it's an amazing recruiting, mechanism.
We've experienced that in the past, and again, not just with MTU, obviously with other schools as well. But it's, I think the key point you're making. I mean, I was in the same boat as you. My dad was working for Siemens in Europe. And then worked for HP for 25 years in Europe. And I was like, I want to go in the computer industry. That seems cool, And then I graduated in Europe. Then I came over here, graduated here with another degree, and then girl as well lived in Michigan or in Detroit. And they say, I'll go up there with your languages, with your electronics degree background and all that stuff. Automotive is great. Automotive. I don't want to work automotive. Well, so was the beginning in 1998, and 25 years later, I'm still here. And you never realized, I guess, how complex a vehicle really is, right? You see it and you say, it has an engine in it, it has a transmission in it, has a few electronics in it, but you really look at it from a system, how complex it is, the different use cases, again, water, ice, all the different, whatever you want to call them. It is an amazing piece of technology, right?
Yeah, and kind of what draws a lot of people in is like, okay, you can go, let's say you go work for, maybe I shouldn't name company names, but let's say you go to company XYZ and they're making like printed circuit boards. Okay, and you can solve the technical issues there, but what's really cool about mobility is if you solve those technical issues on that printed circuit board and your part has to go on a vehicle, cool, you can go get into that vehicle and experience what you've engineered and how you've added value to the customer, or how you've added to solving, say, climate change, right? If you're working on electric mobility and you're passionate about that you can go help solve a tangible problem to society and really feel like you're contributing. And the other thing, right, it's a very expensive product. When people put down their dollars that are hard-earned, they want that product to be robust and to meet their expectations, and you get to be part of that development process. And I was at GM, I worked on transmission, right? Well, transmission goes into a lot of different products. Well, it might be Corvette, Camaro, and those were the really fun products to work on, right? Where you're at the proving grounds and you're driving around and you're like, this is a pinch me moment of, your job. So what is your passion today? Again, you talked obviously with kids, working with students. I can clearly see and feel that. But from a technology side, are you still very much focused on transmissions? Are you taking a much higher approach and into system level type stuff, or? Yeah, that's a multifactorial question. There's the things that put, so to speak, bread on the table, and that's working on kind of systems level engineering, which is this DOE project here at ACM, or American Center for Mobility, testing and validating, is trying to take connected vehicle technologies and automation, fuse those two together over multiple vehicles and save energy, right? So holistic system, vehicle systems, transportation systems, viewpoint of trying to save energy, right? So that's kind of what puts bread on the table, so to speak, from a research standpoint, right? Now, what fires me up from a passion standpoint goes back to my roots at GM transmission engineering, where you like to work on the kinematics and dynamics of new power flows and how to go from electric motor to wheels and trying to solve that problem, right? And so that really doesn't, we don't have a lot of research projects in that, because that problem is mostly solved by industry, and from a proprietary standpoint. But it's really cool because you get to teach that in class and pass that knowledge and ability to do, transmission engineering or even systems engineering down to your students, right? And so then they can go out in industry or other academic, endeavors and use that same knowledge.
Interesting.
Hopefully that answered your question. I got a little bit lost in what I was saying there, but
good. That's good. So when I went to engineering school, again, electrical engineering school, simulation was, I'm not sure we talked about it. Certainly not in school we talked about it. In many other places we didn't even imagine it, right? It was still the drawing board and drawing with pencils and paper and rulers and all that. How important is simulation today when you go to the classroom? Is it like nobody even thinks about anymore taking a pencil in their hand and drawing something up? Everybody jumps right away to simulation. Are you guys making people aware there's still both sides, and understanding every side is important to also use the tools? Talk a little bit about simulation and how that's...
Yeah, so that's a very good question, because I mean, I'm not that old, I'm only 40, but quote unquote, back in the day when I was in college, we used to solve, our dynamics problems by hand, where you free body diagram, you write your system of equations, and you get your one answer and circle it, right? And that isn't even that long ago. And that was pencil and paper, calculator.
Yeah.
Today, in those classes, we teach those same methods because it's very fundamental to the way of solving engineering problems. But then we do, on the back end of that, to show, okay, well, it's great to do it mechanically and methodically on paper, but we don't do that in industry. We have all these software packages. So folded into our curriculum is a lot of software. And we're not trying to teach like specific software. We're trying to show that the software is a tool to solve engineering, much like the process of free body diagram, system of equations, do your solution, right? That the software is now part of that synthesis of the system, and you have to use that to solve your engineering problems, because it enables many more opportunities to find the solution and to do it in a much more rapid way. Okay. And so we do use specific software packages, but again, we're not trying to teach that as the end-all be-all software. It's just the methodology. So in academia, there's this big buzzword of fourth industrial revolution, right? And I'm sure you guys use it. And so academia is like, oh, we need to fold all this stuff. In industry, we've been doing this for years. And so coming back to the university, you can really show the students, this is how we solve these problems, using and leveraging the software to come up with better and improved engineering products, how to use them for problem solving, et cetera. So yeah, it is a very big part, and so you very rarely see students actually writing on paper using their little calculators, right? Like everything's like centered around how do we decompose this physical system, analyze it, use the software and computer systems to synthesize it, right? And the biggest thing is when you and I were in school, we'd always circle, here's the answer, right? Well, we know in industry there's no chief engineer ever comes to you and says, yeah, give me the
answer.
Yeah, that doesn't exist. And so the software and the process we really teach is there's no one single answer. There's better engineering methodologies and better engineering solutions. Right. And it's not like we pit the students against each other who comes up with a better answer, but we just give them ambiguous problems that are tough to solve and let them come up with creative solutions bounded by the physics.
Right. Interesting.
Hopefully that...
No, that's good, yeah. So when you take this DOE program, you alluded to it a little bit, it certainly helps do research. You mentioned it, right? And that's what it's intended for. Yeah. But how beneficial is it really for the students to not only sit in the classroom and, let's say, do something more in the theoretical world, right? Yeah. But get to the ability to go get their hands dirty and see what they calculated, simulated, proofed in the virtual. Now they can put it on a car, drive it on a test track, and actually feel. How critical is that for the students?
Oh, to kind of bring the
whole thing together, sitting in a room doing a calculation, but at the same time then taking it out, downloading some software or integrating a mechanical, whatever it might be, into a vehicle, and now say, oh, okay, no, drives good. No, it doesn't do good. That's what the simulation said. But how critical is that practical experience out of this?
Yeah, it's absolutely critical, because there's some famous model guy who always said all models are wrong. Some are just more useful than others. I'm forgetting the But we carry that mantra to the students and say, it's modeling F equals MA or a physical system, that's all great. And now try and go prove that it represents the real world. Now you'll find the missing components or the stochastic things that'll throw that model off.
Sure.
And also to take and translate their results to a physical design or code, for instance, and try and get a vehicle to do some dynamic maneuver within acceptable customer limits of lateral and longitudinal accelerations. They come to find out like, this is a lot harder than I expected, right? I can't request square wave, inputs. It just leads to very impractical results or undesirable results.
Sure.
So it's absolutely critical that they bring it back to a physical system and try and control it, or try and show that my model does correlate with reality. And that's essentially what we're doing this week. Is our team from AVL has built a systems environment. We've run hundreds of thousands of simulations of what's the energy savings, and now we pick a few of those scenarios and we take our 4 to 6 vehicle cohort, we go out to the track and show that it matches up with reality, as long as all the code is working. And in fact, that's what we're trying to debug today. There's something just as imperfect. And that's
the last minute thing.
Right, and that's all part of engineering. Is like, things don't work perfectly the first time. As many computer scientists, coders will tell you, oh, my code works perfect on the BS, right? There's something in there that's, worth fixing and tuning up, right?
Yeah. So for you, what's the most exciting part about the project from a research achievement? Not necessarily from the technology that we used, or from the ability to give the students again that glimpse into reality, right? Or getting even more excited. What is it that you feel like has come out of this that you guys are going to prove tomorrow that really is exciting for you to see?
Yeah, that's a tough one. Because there's a lot of things that have already been done. That connected vehicle, right? Connectivity, we're using cellular. That's been done. Automated vehicle, right? That's already been done. Showing in simulation that, eco approach and departure from a traffic light, where you have the signal phase and timing, or SPAT. That's all been done, right? What I think's unique here, and I think what the Department of Energy really glommed onto, is that we're bringing all that together and we're answering this fundamental question: what can the synergy of fusing connectivity and automation in multiple vehicles that aren't just light duty vehicles, we're mixing heavy duty and light duty together, how can they work together as a team cooperatively to reduce energy on different infrastructures? And it's you gotta tie many different things in together. And I think what the exciting part is we're able to leverage some of the tool sets that AVL has to link real-time communication from the vehicle to a cloud compute platform that is essentially running a digital twin of the vehicles together. That information that's coming real-time from the vehicle goes in the energy model, then goes into a machine learning algorithm that's also running faster than real time to make decisions on forecasting what the group of vehicles or cohort of vehicles should do, gets beamed back to the vehicles, and they react dynamically to that, and it saves energy. And we're on the 200 to 400 millisecond time frame of communicating from the vehicle to the cloud to the AI making decisions and then back to the vehicle, right? And that's all enabled by a lot of really smart people leveraging tools and linking things together. And it's very cool, and we're doing that all through cellular. And what was really neat on the project is we have Michigan Tech way off in the middle of nowhere in the UP. We have Navistar in Indiana and Illinois, and we have ACM here in Southeast Michigan. We're able to do a lot of debugging virtually because we set everything up on a cellular network, and so we didn't have to have all the vehicles and infrastructure co-located to do our development. And that's very kind of neat. And it's just where the technology I think is going to be applied is, this can become a very cool virtual development tool or virtual system in the loop for OEMs or suppliers to now help develop and validate connected vehicle technologies, where you can set up different infrastructures, either on closed test track or even on dynamometer systems. So I think they're the technology for it to be public-wide of all connected and automated vehicles driving, that's still 10, 15, 20, whatever years.
But it's a glimpse that you guys are showing, right? With
right.
making these different, as you said, as existing pieces were a lot of them were done, but what you guys did, you brought it together so that the 1 + 1 = 3, right?
Right. And now you can really use it as a development tool at the vehicle level, powertrain level, whether you're doing it on a closed test track or on a dyno. I think that's where we can really show that, what we've done with this systems to systems bench through cellular, I think it can afford a lot of development cost reduction.
Yeah.
Because when I was at GM, let's say 2007, that's when I started, we always talked about removing development vehicles from the process because they're expensive. Okay, well, how are you going to do that?
Yeah.
Well, we're going to do everything in math. Well, it's great, but at some point, and that's where I come into using your guys' system on the dyno, where we try to we do some stuff in math, and then we do some stuff in the dyno or the lab, and then ultimately we flash it in the car and try it on the road. And I think what we're doing in this project can really help the math in the lab portion of it before we go try and take it to the vehicles, because test track time, development vehicles are ungodly expensive.
Yes.
Right.
And time consuming as well, obviously.
Right, because they fight you.
Yeah, they do.
Yeah, so
good.
It's probably not as elegant of an answer to that question.
No, it's good. It's it shows. Again, to me, sometimes it's interesting when people say, you kind of said it, right? It's like, well, we didn't really develop anything new, and then the real cool stuff starts. You took all different pieces and brought them together, which suddenly then makes this beautiful system of systems.
Yep.
Where you can really say, yeah, we added several different things that are existing, but with that, it was not 1 + 1 = 2. Again, as I like to say, it really 3, 4, 5. It grew, it mushroomed very quickly. Right?
Yep.
That's cool. Very good. All right. Thank you for your time.
Yep.
And thanks for tuning in, everyone.
Thanks for listening to Reimagine Mobility Podcast. If you liked this episode, please subscribe and tell a friend.